This is the second lecture for Geology 100 Natural Disasters. My name is Dr. Scott Nowicki. Today we're going to talk about earthquakes. We're going to start with defining what an earthquake is, try to visualize what they look like and what kind of effects they can have. We're going to try to figure out where they have occurred on the planet, where they occur around the United States, and kind of project where these might occur again in the future. We're going to spend some time trying to determine what can be expected from an earthquake, and then finally, hopefully we can identify the real dangers that we might face as a function of earthquakes in locations around the world. To begin with, we start in San Francisco in 1906. In the late 1800s and early 1900s, San Francisco experienced a massive population boom, mostly as a function of the California gold rush. Huge numbers of people moved to California where infrastructure was limited. So over a very short period of time, San Francisco expanded drastically. In many places, they threw material, garbage, and dirt and rocks into the bay and claimed land from the ocean. So it was a lot of relatively loose materials that were covered over in masonry that produced much of the city. When this big earthquake occurred in 1906, no one expected it. It was a lot of new implants that came to California, and they had no idea what was underground. The major effects that occurred were huge amounts of shaking that of course destroyed a lot of poorly built masonry structures and brick structures. And then not only that, but pipelines that ran underground, water and gas, broke. Huge amounts of gas were pouring out, of course that caught flame, and anything that wasn't brick and shaken down, all the wooden structures, proceeded to burn. Now of course the entire city wasn't destroyed in this, but there were lots of areas that were affected by both the shaking and the fire, and as a result, San Francisco looks differently today than it would have looked had this earthquake not occurred. Now, the fantastic thing that was occurring at the time was for the first time in California, there were enough people living around the state that when a big earthquake occurred, they could actually map out how much shaking occurred at different locations. This is a map of the intensity, meaning intensity of shaking that occurred as a function of that 1906 event. You can see that it's not a bullseye shape, that there's some structure to it. First of all, the epicenter, the actual location of the earthquake itself, is right here in this triangle, and it's very close to the city of San Francisco itself. And as you go out away from that epicenter, you can see that the intensity decreases. But if you go straight east, the intensity decreases faster than if you were to go north or south. So what we can see here is simply the fact that there is a fault that runs north-south underneath that earthquake. So this is proof for the first time that in California there are these large-scale faults and that Californians should probably pay attention to them. Now, of course, this earthquake was absolutely massive, and it led to a lot of the codes that were established and still in place today in terms of building to prepare for earthquakes. So when we talk about what an earthquake is, it's actually simply a series of vibrations that occur at the Earth's surface that are produced by the sudden release of energy by movement along a fault. So to begin with, shaking, and you have to have a fault. So this movement results from stresses that are built up in the crust caused by tectonic forces. So these tectonic forces are mantle convection. It is the large-scale movement of the interior of the Earth that causes heat to move from the hot core towards the surface where it can be radiated out to space. So the type of movement that we're talking about is mountain building episodes, crustal loading, or volcanic activity, and we'll see some evidence of each of those. The faults themselves are simply fractures within the surface of the Earth along which some amount of movement has occurred, and we can define different types of faults as a function of the different kinds of movements. Now throughout this lecture, I'm going to use the term earthquakes or seismicity pretty much interchangeably. The terms that we need to know include the focus or the hypocenter, and that is actually the three-dimensional location of where the earthquake occurs. So in this three-dimensional plot, you can see that the focus is at depth and in some location within that three-dimensional block. Now the epicenter is what we usually think about when we talk about earthquakes. The epicenter is simply the position of on the surface of the Earth directly above the focus. We use epicenter because that's more of a geographic definition of where these things occur. We often refer to it as the earthquakes as occurring within a city or occurring along a specific fault. So the epicenter is simply the map projection of where the focus lies within the interior of the Earth. Now the slip is the amount of movement that actually occurs along the fault. So it is the distance of displacement from one block on one side of the fault to one block on the other. Now when an earthquake occurs, it actually occurs at a specific point, or at least it starts at a specific point, and then it radiates energy out in all directions. So we're going to use this information to try to determine how we can really understand where and why earthquakes occur. But before we get there, we have to talk about how we actually map them out. So this is a cartoon of a seismograph. We measure earthquakes by simply running these seismographs. A seismograph is a simple device. It is a mass suspended from a spring and a rotating, effectively, roll of paper. So that if there is no shaking that occurs, that paper will simply roll and it will draw a straight line because that mass will stay where it's at. Now if the earth moves up and down, side to side in an earthquake, it will effectively stay in one place when the whole earth moves up and down around it. So not only does the earth move up and down, but that rotating paper roll actually moves up and down as well. So as shaking occurs, it actually draws out this movement up and down on this rotating barrel. Now of course you need 3 dimensions. You need up and down, the z dimension, you need back and forth, the x dimension, and you need side to side, the y dimension. When you have all 3 of these dimensions, you can actually map out exactly how much movement occurs along a fault. Now there are different kinds of waves that occur with earthquakes, and we can define them using relatively simple terms. So to begin with, we have P waves and S waves. The P wave stands for primary and the S wave stands for secondary. But at the same time, a P wave and an S wave actually show 2 different types of movements. So the one on the top with the slinky, this is a P wave. So the crust itself is a relatively solid mass, but it can transmit energy so that the spring kind of acts like the crust. Now if there's compression that occurs along that spring, there's that compressional wave that will move along the dimension of that spring. So here it is, starting that compression, the compression moves along that spring, and at some point probably hits the back end and turns around and starts coming back. So that P is a percussive wave. It is the compression that occurs within that spring. The second kind of wave is the S wave, and the S wave is, here is our continental crust, and an S wave is an up and down motion. So just like a piece of rope, when you whip it up and down, will generate this S wave, and S actually stands for shear wave. So the shearing is this back and forth movement that is perpendicular to the line of travel. We can visualize that by simply showing that there are compressions that move through the ground, and there are these side to side or up and down movements, these shear waves that move as well. A P wave stands for primary wave, but it also stands for percussive wave. These are compressional waves and very similar to sound waves. They're a series of contractions and relaxation of the rock. So motion of the wave is along the direction of the wave propagation. These waves move fast, somewhere around 5 kilometers per second depending on rock type, and they travel through everything. You can hear them through the air, you can hear them and feel them in the water, you can of course feel them in the earth. Whereas S waves, this up and down or back and forth, side to side movement, are these shear waves where the motion is at right angle to the direction of the wave propagation. So the S wave moves up and down even though the wave is moving forward. They move at about half the speed of P waves, and they'll only travel through solid. If they hit liquid, they effectively stop because liquid can't transfer S waves. And then finally, the third kind of wave is called surface waves, and these move only along the Earth's surface, radiating out from that epicenter. There are 2 kinds, Rayleigh and Love. The important thing is that it's very strong at the surface, but it attenuates with depth. This is the Love wave. And then the Rayleigh wave is more of this rolling wave, like waves in the ocean. But again, they're really strong at the surface, but they die off at deeper and deeper depths. P waves, S waves, and surface waves can all be seen in the motion that is detected by seismograms. So that if you have a seismograph running somewhere on the Earth and an earthquake occurs, It takes some amount of time for those waves to actually reach the seismograph, but because of the fact that they move at 3 different speeds, they actually arrive at the seismograph at different times from the same earthquake. Here's the focus and where the earthquake started. All 3 waves were generated at the same time, P, S, and surface waves, but over time the P wave travels the fastest, then it's followed by the S wave, and finally these surface waves slowly make their way at much slower speeds. So that here is the actual seismogram measured by the seismograph. At a couple of minutes after the earthquake occurred, the P wave hits and then kind of calms down, and then a few minutes later the S wave hits, and then the S energy comes down, and many minutes later that's when the surface waves show up. So there's this time dimension to actually mapping out how earthquakes work. The amazing thing is that we can actually use the difference in the arrival times of the P waves and the S waves to really determine the location of an earthquake. So if you have 3 random seismograms around the Earth and they are measuring a single earthquake that occurs, you tend to get trends that look like this. Seismogram A that is located in one location, the P wave arrives at one point, and then a few minutes later, 3 minutes later, that S wave arrives. So there's this gap between the P wave and S wave that's a function of the distance from the earthquake. At seismogram B, which is again randomly located around the planet, it takes longer for that P wave to hit, and then there's a longer gap between the P wave and the S wave. And then finally, at this third location, seismogram C, located again some random place on the Earth, the P wave hits and there's an 11-minute gap before the S wave hits. So we can actually use these gaps in time between P wave and S wave arrival to determine the distance from the epicenter each of these seismograms sits. Here on the y-axis, that is the time that has elapsed after start of the earthquake in minutes, and then along this x-axis is the distance from the epicenter. So simply by looking at the time gap, we can determine that it was 1,500 kilometers or so away from seismogram A, it was 5,500 kilometers away from seismogram B, and 8,500 kilometers away from seismogram C. So we can locate the epicenter of an earthquake by simply using the arrival times of the P and S waves. We need 3 recording stations to determine the location of an epicenter. So there's seismogram A, and it is the closest to the earthquake. If we simply map out the 1,500 kilometer radius, here's that circle. So the earthquake had to have occurred somewhere on that circle. There's the B wave, or the B seismogram, and here's that 5,600 kilometer radius. The earthquake had to occur somewhere on that circle, and then here's the C seismogram. And the location of the earthquake is simply the intersection of all 3 of these circles. That's how we go about mapping earthquakes on a regular basis. Now, of course, we want to determine how big these earthquakes are simply by using the information recorded on the seismogram. We can look at time, and here's the time gap. We can look at amplitude, or how much shaking occurs within these waves, and use those to map out a magnitude. We use 3 different graphs that are right next to each other. On the left-hand side is the distance, or the interval between the S and the P waves. If you were way down here, you would be standing on top of the earthquake. If you were up here, you would be 500 kilometers away from the earthquake. And over on the right-hand side is the amplitude in millimeters. How much shaking up and down, how much literal movement of the Earth's surface occurred. In this case, there is a time gap of 25 seconds between the P wave and the S wave arrival. The total amount of movement that occurred here, the amplitude was 23 millimeters. If we plot here 25 seconds, and over here we plot the 23 millimeters, and we draw a line between them, this is our Richter magnitude. It is this measurement of the size of an earthquake. So obviously earthquakes can be incredibly small, numbers just barely above 0, or they can be very large, 5s, 6s, or larger.